Hello and welcome. This is a video done by Mikhail Tikhonov. This is a demonstration of results of EE278 term project taught by Professor Chang Choo in spring 2016, an adaptive FIR filter. In scope of this project, I have implemented an FIR filter with LMS algorithm as Verilog RTL code, performed behavioral simulation and packaged the code as Vivado IP core, and used it in a simple SoC design to demonstrate the result in hardware. For the rest of the video, I'm assuming that you have a folder with saved copy of my work open on your computer. There are two projects in this main folder, one for RTL simulation and another for SoC hardware demonstration. We will start with the RTL simulation. So, let's open this simulation project folder. This contains, first of all, the folder with my source code, where you can see all the RTL source code, and a sim folder with simulation sources, including the main test bench file. Other folders are the Vivado project folder, which has lots and lots of auto-generated files, and a folder for simulation to dump its outputs to one of the selected subfolders. If you're on Windows, all you will need to do is double-click the project file and it will open Vivado. Since I'm on Linux, I will do so through the terminal. As you can see, the design sources for this project include my filter and the unused IP core, which you can ignore. The simulation sources have the main test bench set at the top, instantiating the filter. Let's look at the test bench. The test bench instantiates the filter, presents a few lines where you can set the parameters of the filter, and has a lot of tasks for doing the simulation, including tasks for opening the stimulus file and dumping data into the output files. The test routine at the end uses those tasks to actually run the simulation. So let's launch the simulation. You can do so by clicking the Run Simulation and Run Behavioral Simulation. As you can see, the waveform has opened. Now you can click the Run All button at the very top and wait for the simulation to finish. The simulation runs through multiple different test runs at different tap depths, but we will look at it once it completes. So let's take a look. The test bench presents a few top-level outputs as analog waveforms, particularly the filter output Y as a teal wave, the data error as an orange, and a difference from MATLAB model as green. Each of the red pulses you see on here shows a moment where the simulation is reset after each test run. So this right here is a single test run at tap depth of 20. As you can see, the waveform converges. Error converges to 0. If we scroll down, we can look at the particular submodels of the RTL code. For example, at the data pipeline. Let's zoom into a single cycle of it. Here you can see a pulse where a new data sample is pushed into data pipeline, and a train of read commands reading all the contents. Internal tap counter right here counts until the tap depth has been reached. That is why you get exactly, in this particular case, 20 data outputs from the test bench, from the pipeline, which is communicated by the valid and last signal. coefficient memory functions rather pretty similarly. You can also see the output train. As a note, the color coding in the simulation waveform is following. Teal colored signals, like these ones, are all the inputs to a particular module. Orange colored are the outputs. Gray is internal pipelining, and green is various internal signals, and also clock and reset. So let's look at what happens with outputs of these two modules. Here we got our data tabs and our coefficients. If you look, they go straight to the LMS as inputs in here. As you can see, the valid and last outputs from coefficient and data pipeline are the valid and last input markers into the LMS engine, where you can see the coefficients as inputs, the old coefficients particularly, and the data from the pipeline, as well as error from the previous cycle. The LMS engine computes the new coefficient and returns the data delayed the needed amount of clock cycles to be in sync with the new coefficients. The reason for doing so is so that these outputs can be directly used by the Mac module as its inputs. Mac module takes in the new coefficients and the data in sync with them, and clears all the previous coefficients. Clears the previous Mac contents and runs a multiply accumulate procedure. The output last signal signifies the output of the Mac. Let me change this to hex radix. Alright. As you can see, the inputs are 16-bit, output is 32-bit. Mac has internal rounding logic, internal saturation logic, but the rounding logic is done externally in the top module. As I mentioned, the test bench allows you to change the parameterization of the IP core. Let's do so. So currently the simulation was set for 16-bit on both coefficient and data. Let's change it to, say, 7 bits on both. After doing so, you will need to relaunch the test bench, the simulation. Let's run the full simulation run again. You will notice that the data looks a bit different now. Specifically, you can see that the noise once the waveform once the error waveform reaches its minimum is now much larger than what we saw in the previous simulation. To conclude our demonstration of RTL simulation, let's look at files done by the simulation. With the current test bench settings, the files will be in the other subfolder. Test bench dumps 2 files for each test bench, for each test run. One file contains particularly the error and Y outputs of the filter. This can be imported into MATLAB. The other file, let's look at, say, this one, contains the filter coefficients at each filter step. In this particular case, we are looking at a 7-tap filter run, so you see only 7 coefficients at each step with 7-bit precision. As a result, maximum you can see is 7F. This can also be ported into MATLAB and analyzed. This concludes our demonstration of RTL code simulation, which demonstrates filter properly operating. Next, let's look at SoC hardware project demonstration. As you can see, this project has a very similar folder structure to RTL project. There is a folder with all my source code, particularly all of the source files. However, these ones are not for the IP core, but specifically for the hardware project. We will look at them a bit later. Note that there is a C file for the SDK software. We will look at this later as well. There is a separate folder which contains my packaged filter as an IP core. If we descend down the hierarchy, we will find those same RTL files from the previous simulation. There are few extra, specifically 3 new RTL source files which implement the interface with the standard AXI bus and hook up that interface with the filter. There are also a bunch of extra automatically generated TCL and XML files which define the IP core's GUI. These are not editable directly. And just as before, there is a folder with the Vivado project and lots of it automatically generated files. So again, if you're on Windows, you just need to double click the project file to open Vivado. Since I'm on Linux, I'm using the terminal command. Let's browse the hierarchy of the project source files. As you can see, there is a top file. This thing does very few things. It does a couple things with board's LEDs to show that the board is alive. And most importantly, it instantiates the SoC block diagram implementing the SoC system. We will look at it a bit later. But you can see the block diagram file as instance in the top file. There are 3 constrained files. There is a pin assignment constraint file, which assigns all the pins of the project. At the bottom, it also has a few constraints in case somebody wants to generate the MCS file for programming ARTY boards on board flash chip. You can see a lot of commented out stuff. This file was simply provided as a template by the Digilent, the manufacturer of the board, and I commented out the unneeded stuff. Another constraint file contains a placement block which forces my filter IP core to a very small location on the FPGA die. We will see that a bit later. And lastly, there is a constraint file which contains auto-generated constraints for ILA probe placement. ILA is an integrated logic analyzer, also known as chip scope, which allows you to capture waveforms in hardware design. We will probably skip that in this demonstration completely, but this is a very useful utility for debugging design in hardware. Next, let's look at the SoC system. So let's open the block diagram. This is Xilinx's kind of alternative to Altera's SOPC system, except it's organized not as a table but as a kind of schematic-like block diagram. What you see in here is a Microblaze CPU, which is an embedded processor similar to Neos 2. It's configured in somewhat semi-default settings. In this particular case, if you zoom in, you can see that it has an interrupt port, a debug port, a data and instruction local memory port, and the XI data port for peripherals. You can see XI interconnect, which has 4 slaves connected. There is UART configured as 9600 baud, which is general default settings. There is an XI timer with almost default settings, except second timer is disabled. This is useful for counting clock cycles as the C program runs. Then there is my filter IP packaged. These are the parameters of the filter mapped to the GUI in the IP packager. And last peripheral is interrupt controller at default settings. As you can see, it has exactly one interrupt connected to it from the UART. Other stuff on the diagram includes local memory of the CPU. You can expand the sub-block diagram to see the block RAM used for both ports. And you can also see the debug model, which you generally want to have. The infrastructure of generating reset and clocks for the system. Note that the entire SoC system is on the 100 MHz clock. 25 MHz is also generated but not used. Lastly, there is an JTAG to XI bridge, which is a second master on the interconnect. This is sometimes useful for later debugging designing hardware. So this sums up the blocks used in the SoC system. Memory map, as you can see, let's sort by the address. This is the CPU portion. This is the JTAG master. As you can see, CPU has 2 ports, or more like 2 categories. There is the instructions group and the data group. Instruction has only the local memory map to it. This is a 32 kilobytes, which contains the program code and the program memory in the same group of block RAMs. Then the data port allows the CPU to have access both to the program memory and the 4 peripherals, including my filter. As you can see, their addresses all start a bit higher up from the local memory. Good practice is to keep the local memory at 000 and put everything else, well, you don't want anything else to intersect with that memory. As you can see, most of the IP blocks use 4 kilobyte allocated bar space, which is the minimum you can do. For the LMS filter, I'm using 8 kilobyte because the top 4 is the output buffer as a single block RAM. JTAG bridge has access to the peripherals, as you can see. This sums up the SoC system. Last thing you can notice is these green markers on some of the nets, including the XI connection to the filter IP core. These are one of the 3 ways to designate some of the design nets as possible ILA probes, which can be later connected to the actual ILA debug core, which is what that constraint file we looked at earlier is for. Next thing we want to do is launch the project's implementation process. That can be done a couple of ways. The simplest is we just click on the Run Implementation in the Flow Navigator on the left. This launches first the synthesis process and implementation. You could also click on the Generate Bitstream step, which would do the previous 2 as well. As you can see now, the synthesis step is running. On my computer this will take about 10 minutes total for everything. So our compilation run is done. As you can see, the implementation is complete with fairly large positive slug and no other problems. You can see bunch of warnings, but also typical in FPGA tools, and in this particular case can be ignored. As you can see, post-implementation utilization is fairly small, and note that this is a very small FPGA. So let's launch generation of the bitstream. We will need it. And while that's running, let's go look at the implemented run. Alright, let's open the utilization report to see hierarchical utilization listing. In this case, we can see everything in our here's bitstream done. Let's close it. You can see everything in our block diagram, and first of all, you can notice total utilization of the entire design, about 5,000 LUTs, or well, let's reorganize this a bit. So I have about 2,000 slices, about 5,000 LUTs. See, total of 18.5 block RAM tiles. 0.5 is because Xilinx block RAMs can be split into two halves, and 5 DSP models, out of which 3 are used by the CPU and 2 are used by my filter. Similarly, block RAMs, 2 of them are used by my filter. Let's look at it in detail. So we have our bus slave port. Well, first of all, let's color the entire filter in a nice pretty color, which will be useful later when we look at device mapping. And let's color the bus slave port as brown. You can see bus slave port uses one of those block RAMs as output buffer, and it also constitutes about close to half of the total slices used by the filter, and very considerable utilization in general. This is a general picture with small peripherals like this using an AXI memory mapped peripheral interface. That's why it's not the most efficient interface to be used for such things. Let's look at filter itself. So here are our 4 key submodules. Our coefficient memory, let's highlight it in blue. Our data pipeline, let's highlight it in red color. Our LMS engine, which we'll highlight in green. And our Mach filter. Note that I'm using highlight leaf cells instead of regular highlight. The point of using highlight leaf cells is so that when you look at the design view, you can actually see the related respective resources colorized on the device view. So let's go back to utilization. As you can see, both coefficient memory and data pipeline use 1/2 of a block RAM. That can be seen right here on the device view. Here is a single 36 kilobit block RAM, which with Xilinx technology can be also partitioned into 2 18 kilobit block RAMs. You can also see that LMS and Mach models use single DSP block by themselves, which you can again see right here. Here's an LMS DSP and here's a Mach DSP block. Unlike Altera, Xilinx DSP models are not partitionable into smaller multipliers, but they do have a bunch of built-in pipeline stages, pre-adders, post-adders, and a bunch of other logic built into them. Other than that, you can see that the biggest combinational logic user is the Mach model, which, as I found out experimentally, is specifically the saturation logic, which probably could be implemented more efficiently. So let's highlight the rest of the design. So here's CPU and its memory. Let's highlight it in yellowish. Let's highlight every debug related module in gray and leave everything else unhighlighted. Now let's go look at the design. Overall picture shows about a third of the or quarter of the FPGA used, with CPU and debug logic being the major utilization parts. Our filter is confined to very tiny section of the die. This was done by the constraint file. You can see the individual slices, small blocks. The left side of each slice is the LUTs, central slice is the carry chain, the right slice is the registers. As you can see, a very good chunk is used by the bus interface, and there is a pretty big carry chain used in the Mac module for the adder. This concludes our exploration of the implemented design. Next thing that you will want to do is set up the SDK, which is a software development kit for the CPU software. In order to do, well, assuming that you have your pre-provided folder with my work, that would already be done, but I will go through this procedure quickly just in case. So what you want to do is you want to first of all go to File, Export Hardware. This exports SoC system characteristics similar to how it's done in case of Altera for newest two projects. Note that you have to either implement design or generate the output products of the block diagram before you can do so. Next, you launch the SDK tool, which can also be done from the Vivado file. Note that both in exporting the hardware and launching SDK, I'm using the defaults, which is good enough in this case. So here is our software development environment, which should look very familiar to those familiar with newest two tools from Altera. So let's do a very similar thing and create a new application project. Name it something more or less creative. EE278 demo software project. Leave everything else on defaults, which means it will be, all the files will be within the auto-generated file location of the Vivado project. And click next. Here we just leave the hello world example to be generated. This will take very little time. Now that it's been created, similarly you can find the hello world C file auto-generated. Now this we are going to need to replace with my code. So let's go to sources and the hello world C code that I developed as part of the demonstration. So let's copy paste the code into SDK file. Saved. Let's run through it very quickly. So it sources a couple of important include files which are needed for operating the timer, and has a couple of constant vectors from MATLAB output. This is our stimulus stored in the program memory. Then it declares a bunch of functions written by me, and it has the main function. This simply calls for particular instances of the main test run function, providing it with the top depths and number of samples, in this case 1000 samples. And of course, before doing so, it prints a nice message of program start and a message of program end. The functions are following. You got currently unused function for printing out the current registers of the IP core. You got the function that pulls IP core until it's idle. You got two functions which reset and flush the filter IP core. You got a function which pushes a single point into IP core and then waits till it's idle. So this is basically a push single sample into a filter and wait till it's done with it. Note that it takes X and DS input, formats them as a single 32-bit word. And there is currently unused function for taking a single output point out and dumping it into UART. This is not used, a different function is used. Then there is a function for running all 1000 or whatever is provided inputs, so it really just loops through the function we just looked at earlier 1000 times and provides it with values from the stimulus vectors. Then there is a function for going through all the outputs and printing them to UART. What this does is that it first reads the status register of the core to get its output buffer pointer, which is stored in the top 16 bits. And then it prints you a nice message telling you that it's going to print all the error and Y pairs. And then it loops through all of the entries of the output buffer, reads them from there, extracts Y and E values and dumps them into UART. Then there is a function for setting up the LMS filter IP core before each run, which basically resets and flushes the core and sets the top depths by writing the top setting into the top 16 bits of the control register. Then there is a function for setting up the timer. This uses Xilinx pre-provided generic functions for controlling the timer core. And finally the main test run function, which is what is called 4 times in the main routine with different top depths. This takes a number of samples to run and the tops. Then it uses all the previous functions to do following. It sets up the FIR filter, it sets up the timer, prints some nice messages, then it starts the timer, captures the time count of the start, runs through all the samples without printing anything, because UART takes forever to print everything. Then it captures the time it finished, the filter finished going through the last sample, pulls out all of the 1000 points out of output buffer into UART. Note that the output buffer is 1024 deep, and since in this case stimulus is 1000 points, then you can simply do this routine in one time, because all of the outputs fit in the output buffer. And it also captures a tick of when it's done printing stuff, and prints some stuff about the clock cycles. And that's the end of the test run. So that's your C code. Now at this moment you want to make sure that your board is connected to your computer. So let's go back to Vivado. There are a couple ways of programming the board. You can do it from SDK as well, but let's do it from here. As you can see, there is a hardware manager which we're going to open by clicking the button here. And you do the auto connect in the open target menu. And assuming all your drivers and everything else is set up correctly, you want to see the FPGA part as a result of the JTAG scan. So let's program the device. From the right click menu, click program device. This will be already populated with the image bitstream and debug props file from your implementation run. Click program. FPGA is programmed. By the way, notice that you had some error message earlier. That is because my board has other design pre-programmed into its flash memory. So the Vivado is noticing that the ILA probe mapping does not match between that design and the design that we just generated. You can see the new ILA window, which shows all of the ILA probes currently configured, where we can set up the trigger. Let's put it on the new XD probe. This is a pulse which goes to the filter whenever CPU writes a new X and D pair into the register. So in here we're going to set it up to be equal binary rising age transition. And let's say that the starting point of the trigger is say 20. You can force the trigger. Right now there will be nothing in the waveform because the CPU is not doing anything, it's not programmed. Let's arm the trigger, but ignore this for now. So this is basically waiting for whenever CPU writes to the filter, which is it's not going to do until we program it. Let's do so from the SDK. So the build is done, which means from the right click menu, very similar to NEOS2 development environment, you click on the launch on hardware system debugger. You don't need to do any other special menus, this will take care of everything. So program's launched. At this point you need a serial terminal. Normally, if you're on Windows, you can just go to SDK terminal, click on the plus sign, configure the baud rate as 960 and select your port. Unfortunately on Linux, the SDK has a few problems, so I'm going to use a standalone program for that. So let's configure. This is a GTK term, which is one of the very common serial port communication programs, similar to PuTTY, similar to what was the other one? Minicom. Yes, PuTTY is the Windows version, Minicom and GTK are the Linux programs. So let's configure the port to be 960 port, USB port. Everything else is on default. Connect. As you can see, the C code starts to execute the code. We got the initial program start message, we got the and already finished the run of the 6 taps, dumped all the points and is doing the 12 taps. Note that in the console it's not in the particular GTK term, it's not printing all of the points into the terminal, it's running over and over them. You can easily dump that into the console log by setting up the login option. In the SDK terminal you'll actually see all of those in your log directly in your terminal anyways. So let's go look at ILA results. As you can see, ILA triggered right here, which was set which triggered, where is that? Right here. Let's highlight our trigger signal with something notable, and let's highlight the signal which shows when the filter is done with a different color. So as you can see here, let's look at let's look at 2 cycles. So here CPU enters first point, filter is done. All this time right here is CPU getting the next point. Here it enters the next point. You can see some bus traffic of the, well, first of all you can see some internal signals right here. Let's move them down, and you can see some of the bus signals monitored. I'm not going to go through this right now, but You can see the general pattern of writing and reading the registers of the filter. Let's go back to the terminal. As you can see, at this moment the program finished all 4 runs: 6 tap, 12 tap, 17 tap and 24 tap, as it was programmed to do in the C code right here. The results of the run, if you dump them into log and save the E and Y as a text file, you can import into MATLAB and plot. You can see that plot in my project report, which shows that the filter does a proper operation similar to the RTL simulation. The filter converges for 24, 17 and 12 and fails to converge at 6, similar to simulation in which it was convergent at top depths of above 9. This concludes the demonstration. As you can see, the filter works in hardware.